Okay, so I'm going to talk about, humanoid robots, and I'm going to talk about how the warehouse is kind of the entry point to get out into broad daily life and into your home. When we started the company, which wasn't that long ago, and we pitched to people and said, humanoids are going to be part of everyday life. This is real. Very few really kind of believed us. Bruce did, but it was an uphill battle. A lot of conversations are like, yeah, that's 20 years away. But we're starting to get the whole world starting to recognize just how big this is going to be. And you can see that these numbers vary wildly, right? I think there's a 38 billion number, and bigger than the automotive industry, which I think is a very realistic, thing to say and give you an idea of the scale. $7 trillion market. I don't know. That's too big for me to count. I don't know what that means, but it's big, right? And there's a lot of money going into this right now because people are recognizing this. So we basically spent a few years and looked at hundreds of use cases to find the right match between the technology that we knew was going to be generally useful in the world in some way, and a market where we're going to be able to make money at the very beginning, like a beachhead market, right, to get started. And we found really that moving totes in warehouses is the right match. It's just something that a humanoid robot that we can build will do useful work now and early. And then this is kind of how we get started. So humanoids are going to start in these industrial settings, and we'll talk about why, logistics, manufacturing, that kind of thing. And then quickly expand to other industries that are less structured, require a lot more generality in the perception, the intelligence, the decision-making, but also the manipulation, the locomotion, the mapping, navigation, everything else that it needs to do. And it's going to require safety is a really, really big deal, and we'll talk about that a little bit. Eventually, we'll get in the home. But we're really not there yet. And I heard someone the other day said, until you can prove that the robot is not going to fall on a baby, it's not going into the home. So that's a pretty high bar, It's going to be a while, but we'll get there. Just to be clear, right, the home is the very highest standard of safety, capability, manipulation, and maybe I'll say safety again. The warehouse is just how we start practicing that. Okay, so that's how the industry looks. That's how we see this opening up. But about the robot, I'm going to talk about what a humanoid will look like that's going to enter this industry. And not necessarily just our humanoid, but kind of first principles, physics, reasons why it, first of all, can look sort of humanoid and is useful for that reason, and what its features will be. Similarly, I'll talk about what an embodied AI looks like, what the kind of structure of that AI looks like. And I'm, again, trying to look at it from kind of a first principles. This is not just an engineered system that we built. It's how all of them will look for, reasons that everybody shares. And then I'll talk about safety and why you really have to overcome that hurdle before it's possible to scale. All right, so story number one, how to build a useful humanoid. It's not going to look like that. There is no reason to build a robot that looks just like us, and that is not what we're trying to do. We are trying to build a robot that is multi-purpose, that can operate in our spaces, that is human-centric. And because in the built environment, there are so many different use cases and tasks and things you can do, the way the space exists, having a robot that's roughly our form factor, but more importantly, can also follow the same workflows and do the same kind of manipulation, there's a lot of opportunities for multi-purpose. It's a really big opportunity for a form factor like that to be multi-purpose. I can't think of another way that you would have a machine do so many different things, because we've designed the world around us. But when you really kind of dive in and start to look specifically at what is it going to do, we talked about moving totes in a warehouse as a starting point, and then that leads us to some actual requirements. So we're kind of like spiraling in. This is why I said it's a match between the technology and the use case. You don't start with the use case necessarily. You don't start with the technology. You end up trying to find that match. So in order to do this, this use case, we have to lift 25 kilograms. That's like the OSHA kind of regulatory limits, and that's what a lot of these warehouses and factories use. We need to operate in narrow spaces. They're little aisleways, because a person can go there. And be able to reach up high, to lift these things up over about 6 feet high and pick things up off of the floor. So it's got to have this, this huge workspace, which is really one of the advantages of this humanoid. It's going to need to have at least 90 minutes of battery life between its self-charging. And boy, all of that starts to really constrain what the machine is going to look like and what it's going to do. So the first one I would say is if you're in a narrow footprint and you have to reach up high, it is going to be balancing. It's going to be dynamically stable, just like people are and animals are. A lot of robots are statically stable, like a table or a chair. The problem is, unless you've got a really big, really, really heavy base, anytime you lift up something a little bit heavy, the robot's just going to tip over. But if you're balancing all the time, it's fine. You can get under it and change your center of mass to be underneath your combined center of mass with your load. Now, we shouldn't necessarily jump to legs here, right? If you're dynamically balancing, I think that's the thing maybe I can convince you is definitely necessary. You can do it on wheels or you can do it on legs. But if you're doing it on wheels, it's something like a ball bot or a Segway, you still have to be able to bend down and pick things up. So you still need kind of a mono leg or something like that, right? And so you start to get close to the complexity of a bipedal pair of legs anyway. Another thing that's interesting is with legs, it's non-holonomic, which just means it can go in any direction from whatever position it's in. And you can't do that in a Segway. You can't go sideways in a Segway. In a ball bot, you have no yaw control because it's this tiny little contact patch. Obviously, terrain matters, okay? Maybe it doesn't matter in this first use case, but down the road, for this vision of human-centric robots, yes, you want to handle stairs and things like that, so that's a reason for legs. But what's really interesting is that legs are actually a lot more stable than a wheeled base, even for dynamic stability. And just imagine if any of you have ridden on a Segway or hoverboard. Do you feel more comfortable having somebody come and give you a push when you're standing or when you're on a hoverboard or a Segway? The Segway has to accelerate on the ground to get that wheel underneath your center of mass. And if it just slips a little or doesn't have quite enough torque or hits a little bump, you just end up careening into things. And that's true for robots too. I'll show later on kind of us pushing the robot around a little bit. So I think the hang-up for most people on legs is actually that they seem complicated. But honestly, that's just kind of a science thing. Once you know how to do it, it's not so hard. And this is what I was doing 10 years ago at the university. We were looking at this as a science problem. We were looking at what's a math model that represents animals. This is pulled from the biomechanics community, just trying to understand the physics. And we built this machine, Atreus, which is an acronym, assume the robot is a sphere, and this is the math model. The robot is that math model, like directly, literally. The simplest controls you can imagine, stupid heuristics. But this is the first robot in history to reproduce the dynamics of a human walking gait. And that data for that is right there. That's the force plate in the lab, actually stepping on the force plate right there. You can't really tell the difference between a graduate student and the robot. So that's interesting, but that's just a symptom. The other symptom is that this robot, once all of a sudden we captured that, it kind of settled into this self-stable behavior, we could take it outside, and it was very robust. There's no sensing, there's no planning. It's just moving the leg back and forth and bouncing kind of in this self-stable dynamic behavior. And this is pretty cool. You can't predict that kind of foot placement right there where it caught the edge of the foot and lifted up over the top, and still it just takes it all in stride. So this is the foundation. When we did this, we say, okay, I think we know how to make robots get around in the world on legs, and robots are going to be able to go where people go, and now what's going to be possible when robots can go where people go? And this is when we founded Agility Robotics. So we've been doing some work since then. There's an evolution of robots up through Cassie, our first product that we sold to universities as a research product, and up through all the digit robots. And we continue learning. So this one's really interesting. We've just learned this. And I'll try to explain it, but it's really it feels a little bit nuanced. So digit needs to lift with the correct form. This leg configuration we have, it comes straight from, you saw the Atreus leg configuration, it's just a 4-bar linkage. For lots of reasons I won't go into, we ended up with this, but it's all first principles. It ends up looking like a little bit of a bird, like a bird, but we didn't do that on purpose. It's very good for mobility. It's very good for simple control, because you just have one motor extending the leg. It's really nice because you can walk up to a shelving unit and you can squat up and down and nothing's in your way. The knees are kind of behind you. But all of the torque is on this one. This is, by the way, that's the hip joint here. This is the knee joint here. This is like angle joint here, or at least the analog to it. And then this is, we call this the tarsus, we call this the shin, we call this the thigh. So it does have an analog to it, to bird anatomy. But you know, if you try squatting up and down and keep your back, you know, flat like it's against a wall, you end up putting a lot on your knees, and I can't get down very far, and it feels very weak. That's what we're doing right here. And it's just not something we really recognize until we notice, hey, the torque's maxing out here. We're getting, you know, 80 amps, which is kind of the limit of our power electronics. What can we do? We realized, just like people do, if we just lean the torso over and now use that big motor we've got at the hip, we can split the torque between the hip and the knee, share that torque. This works if it's 2 links or 3 links or 4 links. It doesn't matter the leg configuration. You'll just have to trust me on that. But whatever we do, if you lean the body over, this is how people do a deadlift, you know? And you can lift incredibly heavy things. It's pretty unique in the animal kingdom, being able to lift heavy things like that. And we need to be able to split the torque to do that. We also need to get pretty low to the ground. And the problem, the real kicker here, because again, I said with this configuration of leg or any, you can split that torque. The problem is, try to imagine when you lean the body over, the hip has to go backwards because the center of mass still has to be over the feet. When it goes backwards, the knee goes up and the ankle goes down, and the ankle hits the ground. So we can split the torque, but we can't get very low because the ankle hits the ground, interferes with the floor. And that is just fundamental to the kinematics of the machine. So, you know, I've been trying not to build a humanoid. I'm trying to build a human-centric robot that can go where people go. But here we are with bipedal, dynamically balancing. Bird legs are great for locomotion and simple controls, but we are lifting things. We are doing manipulation. We are going to build a robot with a 2-link leg, thigh and a shin, like a person. But we're not copying a person. We're doing it for actual reasons. I just think that's really interesting. All right. So the next one is thinking about why would we have a torso that looks like a person? Well, our first product was this Cassie robot. It's a little basketball. We actually had problems with inertial actuation. Like the robot would twist when it was running, and the primary failure mode, when it would fall, is the orientation and the velocity would diverge. And it would be stepping sideways and then fall over. And we didn't have, these are little feet. There's not a lot of kind of control authority on the ground. And there's no other control authority at all. Plus, anytime you jump or you have both feet off the ground, the legs are most of the mass. So this little basketball spinning around, you just have nothing to react against. We also needed to put a lot more stuff in there, more computers and more batteries. We needed to mount sensors on it. So, you know, we started thinking about spreading out forward, backwards, sideways. Again, we're operating in narrow spaces. The other thing is that having that torso on top is actually incredibly useful for starting up. You know, how do you start? If you're on a Segway, you have to wheel the robot behind you so you're leaning forward, then you can accelerate. But with the torso like this, you don't have to step backwards like we did with Cassie. You can just lean the torso forward, and you know, that allows you to accelerate in the direction you want to start going or start stopping. So having the upright torso was really valuable. Also, it's slower in how it moves, like when you balance a broomstick versus balancing a ruler. So again, we're kind of pushed towards something that ends up looking a little humanoid. We now are bipedal, humanoid legs, upright torso. All right? Now, why do we put arms on there? We could have used an elephant trunk or tentacles or, you know, any number of things. There were 3 completely independent trains of thought that led us to mounting the arms where they are. So I'll start with inertial actuation, okay? Again, I mentioned that we have trouble with yaw control, and the robot would twist sideways and things like that. And we thought about adding a tail, you know, like a velociraptor or something like that. But, you know, that tail is there so that when they jump, they can reorient their feet for landing. We don't need to do that. We need to control around the center axis. And it turns out if you use a bilaterally symmetrical pair of tails and you do this, you can control yourself around the yaw axis perfectly and very cleanly. The other thing you can do is do this, and that's controlling your pitch. You know, people windmill their arms in order to balance themselves. These are just right for giving us really good inertial actuation for our mobility and our locomotion. Also, this robot is tall enough that when it falls, it doesn't matter what kind of shells you have on it. The padding needed to be like 9 inches or something like that so that the G-forces would protect the circuit boards inside, would be low enough. And that's too much padding. So we kind of determined we need to be able to catch it with the arms to decelerate over that space. So now where do you mount your manipulators so that you have 360-degree coverage no matter where the robot falls? Well, you know, these are a good location. And then, of course, bimanual manipulation is kind of the third thing. We have the opportunity and the ability to pick up really big things that a single manipulator, a single arm, can't do, can't lift. And having the kind of the workspace and everything in front of you and where your sensors are, it's really the right thing. And then we needed to keep them, well, they're high, partly for the falling and the inertial. They're also high to stay out of the way of the hips. So it all kind of works pretty well. So nuts. Now we're at bipedal, humanoid leg, upright torso, arms where a person goes, as we try not to build a humanoid robot. The last step, right? We added a head to the robot. How could we possibly need a head? Well, a number of reasons, but one is industrial design matters a lot because these robots are human-centric. They're going in human spaces. They need to be able to communicate with humans. They need to, people are going to feel a certain way when they see this. They're going to have expectations of the robot. You know, in their first half second of seeing it, they're going to have expectations of the robot. And as they interact with it, they're going to have expectations. When it doesn't have a head on it, people think it's headless. Obviously, this thing doesn't really need a head, but it's headless. So that was one thing that got us thinking about it, and we said, okay, what can we design such that it doesn't look like it's headless? Maybe it can be like a Monsters, Inc. kind of monster, something like that. But it turns out, hey, our sensor LiDAR is right there. We needed our antennas and other things above the LiDAR. We needed some cameras to clear the shoulders. We ended up with a head. But now we're also able to have, you know, a really intuitive interface so that even though it doesn't look like a person, it's a very simplified thing that can kind of indicate that the robot is on, that, you know, which direction the robot's about to go. I've heard that the eyes lead the action by something like 2 seconds often in people and how they move around. And also just the general awareness. When the robot is standing, a lot of people think of it as an inanimate object. They don't really register it in the back of their mind unless they think about it as something that's alive. It's like a table or a chair, and then when it moves, it surprises them. And then that surprise is how you hit the uncanny valley, and you lose trust, and people don't like it. So you don't want to surprise people. So having the eyes kind of blink and all this little bit of motion all the time really helps with that. People kind of register it as a thing alive that might move anytime. And I think industrial design is why we get to be on the cover of Time magazine and things like that. So it's really important. It influences people and how they feel. Okay, so to wrap up that section, to meet the requirements of the task for the only rational market that's the beachhead market for humanoids, we need to lift things up high and off the floor. We need to operate in these narrow spaces. We need to lift heavy weights. All of that sends us towards bipedal, upright torso, bimanual, a heavy robot, by the way, because if we're lifting, you know, 25 kilograms and have 90 plus minutes of battery life, and we've got to lift these things up high, it's a sizable robot. It's going to be over 100 kilograms. And it also turns out that the torso is mostly full of battery. There's not a lot of room there for additional actuators and additional things. It's like 80% battery. So in order to do these things, we will not be doing backflips with our robot. It's a very different purpose. All right. Story 2. What does an embodied artificial intelligence look like? Most of the time when people think of AI, I think they are talking about a semantic AI, like a ChatGPT or something like that. And that's because this is just a new surprise in robotics. By the way, even when we started Agility Robotics, we were really focused on this physical intelligence, the controls, the dynamics of the hardware, making sure the hardware enabled even the possibility of controlling it to do the things we wanted it to do and working our way up. I thought it was going to be decades before we're going to have the intelligence to know what a light bulb is and have some context around how you might reach for that and things like that. And then language models just came out of nowhere, at least from my perspective, I think from a lot of people's perspective, and all of a sudden, this kind of semantic intelligence is a commodity now. We can hook up to any one of a number of open models and have our robot kind of understand human context and what's going on in the world. So that's a real accelerator, and that's very, very cool. But just here, I want to kind of point out the difference between semantic intelligence, which is like the brain in the box. It can output things like the IKEA instructions for how you'd assemble a piece of furniture. The physical AI is a thing that says, I have 50 degrees of freedom in my device. How do I actually grasp a screwdriver, apply the right forces, the right impedance control, screw the screws in, and so on, and follow the instructions that are provided by the semantic intelligence. And most people are ignoring this part. Most of the big companies that are really doing AI are up here in the semantic AI, which is fine. People are starting to notice this, and we're working on it, so we'll get there. To break it down a little bit more, I think of this hierarchy where there's the physics at the bottom. This hierarchy, by the way, is sort of differentiated by how fast something happens. So in the physical realm, it's faster than, say, 2 kilohertz. It's things like impacts with the surface. And way up here at the top, it's like, you know, where do I need to get to on Stanford campus? Or how do I make a pizza? Or things like that, which once a second, once every 2 seconds is fine. You can be updating things like that. And also the amount of information, right? So that sort of context is the entire published content of the internet and all kinds of human context and awareness. But down here, for what happens when I make impact with the ground, you need almost no information. And so those two things, kind of that 2 inverted triangles, determine this hierarchy. And importantly, they determine the appropriate tools that can be used in order to solve the problems at that layer. So I'm going to walk through each of these. OK, so starting with physics, this is, you know, again, what happens when you make unexpected contact with a surface. So if you've ever had experience with a CNC machine, as it's moving around and accelerating, like the ground shakes because the acceleration of this big steel plate is so high. And if you ever run the, you know, the tool into the plate, it breaks things badly. Industrial robot arms are like that too. They're very, very much position control based. Humans don't interact with the world like that. And there's huge differences in the physical system that enables that. The kind of backdrivability, the force sensitivity, the compliance in how they interact with the ground. This is not something that you can just have an AI in a black box spit out a robot design yet. There's a lot of AI tools, but still, Ken Goldberg calls this good old-fashioned engineering. You still have to have people who really understand physics, understand dynamics, understand manufacturing processes and methods, understand how to make the best kinds of actuators, and by best, I mean most appropriate for the thing you're trying to do, which is incredibly nuanced. And then design a machine that, again, for which it's even possible to do the controls you want. I see an awful lot of robots, maybe 99%, where it doesn't matter what software you write on it or how good the software is, it won't be physically possible to do the things that people want to do with them. OK, this is an example of what Digit can do because of its hardware. And comparison to some early work, this is a collaboration I was doing with Monica Daly at the Royal Veterinary College. And the bird, of course, run down this runway 100 times and stepped on solid ground. And then this time we surprised it, moved the force plate down and this tissue paper across the top. So then we say, OK, what happens? Well, the bird hardly even slows down. The foot just extends all the way to the ground, and then it keeps going. And this really indicates a measure of force control and compliance. So at some point, the bird just said, OK, I want to apply some force to the ground. It doesn't matter where the ground is or when it makes contact. It's going to make contact at some point and then keep going. That's where you get this incredible robustness to whatever the terrain is. You don't have to think about it too much, and it's sort of self-stable as part of the dynamical system. Well, Digit can do that too. And we just wanted to show here that, you know, maybe, I don't think the perception is even on here, but at least visually we can show you that the robot can't see that there's a hole in the ground. Still, we have some very good actuators right there that we can do very high bandwidth force control with. We place the foot on the ground. We say, OK, start applying force. If the ground isn't there, it just extends the foot into the ground until it does make contact. So, you know, you need the hardware to even enable the force-sensitive controls, even if it isn't a position-based thing. All right. Stepping up then to controls. This is coordinating all the individual joints, like coordinating the ankle and the knee and the hip and the elbow and everything else. balance, joint coordination. And this necessarily has to be learned in simulation, eventually in real life, because every robot you design, because it was made with good old-fashioned engineering, is unique. And so you have to think about what is the right answer for all 50 position sensors and your inertial measurement unit and other things. Take that sensor input and then calculate the torques that you should apply to every of your 50 motors 1,000 times a second. There is no example. There is no source of data. There is no right answer. You have to invent that right answer, and you have to create that right answer. And so the only way to do that is to explore. And that's what reinforcement learning is exploring. And I think it probably takes too long in real life and breaks robots, so you have to do it in simulation. Eventually, you could do kind of the final refinement in real life, but I don't think the community has really started doing a whole lot of that just yet. But just want to point out, this can't be done with data. This can't be done with teleop. This can't be done with extraction from video. This has to be done with the unique dynamics of the robot and explored in simulation. And here's some examples of behaviors that we had to learn. This is the one I told you about, where I think this is quite a bit more stable than wheels. And you can see the robot doing some interesting things. I mean, it sinks down and gets low to the ground. This is not a model-based controller. This is just trained in exploring. The model with the ground is very poor, so this could be different surfaces. Whatever weight it's carrying in the bin, it needs to be robust to. But I don't know. This is very clearly the future of control for dynamic behaviors, doing reinforcement learning kinds of things. Here's another behavior we had to learn. This is what you're going to see here is digits. We've got a trip line. We're being a little bit mean. So the robot's going to fall, and you can see it puts its hands out to catch it when it falls. And then it's turtle. It's on its back. It has to get over and then get back up. And we learned that behavior because it's not something that engineers can just write down, know the answer to for how to do it. We had to explore that in simulation and had it figured out on its own. All right. It did get up after that. I cut it too short. All right. So now the next layer up would be planning. And these are things like, how do I pick up a mug? Do I hold it by the handle or pick it up by the top or reach it around the side? Or when I'm walking through a boulder field, what's my three-step ahead plan of where I'm going to place my feet? You have to have a lot of knowledge about what's going on down here so that you can plan appropriately, and you have to have a lot of context from the things up above. But this is in the 20 to 30 hertz range. Now this is where some demonstration might be useful because someone can teach you how to do things and you learn them much more quickly when you've got that starting point. I think the same is true for robots. So all of the kind of extraction from video and the teleoperation and the motion capture, this is the only place where I actually think that is useful in kind of that planning layer. And so if you have robots that already have a controller and already have the hardware and you just give it kind of XYZ coordinates, this is the sort of thing where each picking of just random things in a box or folding clothing or things like that, this is a really powerful approach then, where you can train things up. But it doesn't solve any of these things down here, the actual controls or the physics for the robot. This is just an example of our planner. Digit knows there's got the virtual twin here, or the digital twin of the world. It knows how to grasp that tote, slide it off the thing, pick it up, and what it's supposed to do with it, carry it over at a high level, and the planner is figuring out all the steps to do that. And then, of course, the low-level controller is coordinating all the joint torques in order to achieve it. And I just like this video. It's just a close-up of the same thing. How do we pick up that tote out of the AMR? Digit didn't figure this out on its own. This is the engineering team trying all the different things with stick arms and then teaching Digit how to do this. And so now Digit kind of has that plan for how it would do this kind of grasping. So learning by demonstration here. In this case, it was a little bit more manual than just a big black box, but it'll get better and better over time. All right, and then the next layer up, of course, is cognition. And I said, language models, vision models, the entire published internet. And here's a demo of that where, you can see here the train of thought. So I think Pross over here was talking to the robot, said, pick up the box with the heaviest animal on it and move it to the tower in the front row that has the closest number to its weight in tons. So a little complicated, but I need to know what items are present. I need to determine the weight of the animals depicted in the boxes. I know that the hippo is the heaviest animal. That box is on tower 7. It's going through this whole semantic train of thought, and then it's basically programming the robot to go here, grasp here, pick this, go there, place there. And this was a very, just a couple of weeks kind of thing to put together to stitch, again, a commodity language model, commodity perception model, onto our robot's physical intelligence and the ability to balance and move and plan. Powerful. And I'll just touch on this, but we're going to have hundreds of robots and then thousands of robots and then millions of robots, and they all need to kind of coordinate. And people coordinating as teams, it's a lot harder because we don't have Wi-Fi, but robots do. So we're going to be able to coordinate all the different humanoids with the AMRs, with the warehouse management system, with the people that are going to be working alongside these robots. And this picture is Agility's ARC software, which is the whole fleet management coordination software for deploying these robots in warehouses. So coming back then to bring it all together, right, we've got the different layers. Again, they happen at very high control rates here, thousands of times a second, to much slower thinking about things. Different tools, cloud, language models, learning by demonstration, reinforcement learning and simulation, and then final refinement in real life, and then actual just hardware design. There's a couple of really, beneficial things about it. Before I get to that, think about learning to play the violin, okay? First, at the foundation layer, you must be able-bodied. In order to actually play the violin, you really need all of your fingers. You need to be able to reach around the violin. You need to be able to have good hearing. There's a lot of things that you need as a foundation to be able to play that well. The next step is your teacher teaching you how to hold the bow, how to hold the instrument. But if that's all you've got, you're going to be a terrible violinist. You might be able to make some noise from it and do the very first things. But in order to get good at it, your teacher's told you what the answer should look like and what it should turn out like, and you can watch recordings of what it should be. That's your cost function. Now you need to do the reinforcement learning, which is the practice, practice, practice piece of it. You have to explore the relationship between your own body, the tendons, the force sensing, your neural connection, the fat pads in your fingers, all of this nuance in how to get your body with your instrument to sound close to the way you want it to be, the way your teacher is helping you with it. So practice, 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 learning by demonstration, and then up here, this is your broad awareness in the world of like, why do I want to play the violin, and what is a performance, and things like that. And up here on the cloud you're playing in an orchestra. You've got an orchestra conductor, you have all these other instruments and teams that have already gone through all of their own stacks like this, and different methods in order to do this. So I guess all this is to say, I fundamentally do not believe in pixels to actions learning, where it's just a big black box that's the silver bullet magical AI that solves your problem, and now your general foundation model can control all robots. I do not believe in that. I believe that these are some very, very powerful tools. I think it's important to use the tools, the right tools in the right place. I think that robots are always going to be a large engineered system. We're just going to have more and more powerful tools to engineer them with. I think one other thing I forgot to mention is that this hierarchy isn't unique to AI. That's true for any robot system, and it's true in biology. It's why we have the different kind of, feedback between our tendon and our muscle. Locally, we have, of course, muscle dynamics with our springy tendons, like your Achilles tendon. That's really intentional and important. Reflex levels at the spinal cord, and then all kinds of structures in your brain for different speeds and different rates that do these different things. So this hierarchy, I think, is vaguely and broadly applicable across doing physical things in the world and embodied intelligence generally. All right. So finally, I'll end on story number 3, safety, as really the key to scaling all of this. The point is that no matter how capable your robot, no matter how sophisticated it is, if it cannot operate safely around people, and I mean safely in a provable way, not just something where you're like, yeah, I think it's pretty safe. Because I'm that way now with our robot, and I get in trouble all the time because I want to go touch the robot and mess with it, and they're like, stop, don't do that, it's not safe, you're showing other people that then they want to do it. I understand. We actually have a lot of robots now and a lot of people, and you know, they are heavy and they are 100 kilograms, and at some point there are pinch points, there are all these things. We have to prove that these robots are safe. We can't just ask people to judge it, because if they're going to go in a home, they're relying on us to tell them that they're safe. And safety is, it's less exciting for most roboticists than, you know, making them do backflips and things, which is cool. Safety is really, you have to be so thorough in order to go through every pinch point, every risk of how, you know, your toe might be crushed, or, you know, it falls and slides and runs into you, all of these things. And typically, you know, they're not going to take your word for it. You have to go through this hazard and risk assessment, and it needs to be validated by a third party. There's companies that do this, like TÜV Rheinland and others. And usually what happens is somebody solves it the first time, and it's like a 150-page document that goes through every possible thing that could go wrong and how they're mitigating every single possible risk. TÜV Rheinland goes through that and extensively, and it costs like millions of dollars to have them do this. And then they validate and put their stamp of approval and say, yes, they have a plan to mitigate these risks. And then that becomes, you know, through additional committees and years and everything else, that becomes a regulatory environment. Someone solved the problem and showed how to do this safely, and now there's a regulation that everybody can, you know, follow that regulation, and then insurance companies and everybody else understand the risk that they are taking. So that's what we have to do, and that's what we're doing. Now, we talked about this. Dynamically stable robots are going to fall. This is unavoidable, and certainly we do it a lot. It has to be okay for the robots to fall, and not just avoid damaging the robot, but you can see that might, if you were laying on the floor right under it, which, I mean, when there's 1,000 robots out there in people's homes, that kind of thing's going to happen. That could cause injury. But there's also judgment errors when you have robots in more general environments. You know, you see the robot bringing you tea. How do you make sure that the robot doesn't pour hot tea in your lap just because it, I don't know, made a mistake about whether the tea was hot or not, or I don't know, had a weird sense of humor because it's an LLM and who knows what it's doing, right? Or it's time to do laundry and the puppy was in the dryer and the robot didn't realize that. Man, it's hard to prove that you're not going to make those kinds of errors or mistakes. Remember that these robots are strong enough to do useful work in the world. And just to like other people and pets and things like that, that amount of force is enough to cause harm and danger. So when you're in your, you know, your friend's home and there's a really big dog, you are trusting your friend to know that dog, and you're trusting the intelligence of the people and the animal around you to know what touches are appropriate, what aren't, and what behaviors that are okay. And this is even aside from things like, is it okay to hug somebody? You know, this is like basic safety kind of stuff. I don't know how to solve this one. I mean, you know, cobots don't choose at all right now. Cobots are bolted down and they kind of limit the force that can possibly occur in an industrial setting. But a balancing robot, it's not possible to do that. They can still fall. Okay, so today, in order to deal with that, you know, what are your choices? You can either limit the speed and force, which again, we can't do with a balancing robot, or we have to separate them from people and have physical barriers, which is how we get these into the warehouses at the very, very beginning. And that's not scalable. You can't like put you know, a cage in a cell around these things. Then why are you doing a humanoid robot? The whole point of a humanoid is to be human-centric and get into human spaces. So how do we do that? To get into human spaces, we have to be able to detect people. And I mean detecting a person, like a person is standing next to their identical mannequin, and you can tell the difference between which one's a person and which one's a mannequin. We need an independent supervisory system. So there's a system on the robot that's completely separate from the whole robot controller that is observing it, making sure it doesn't break any particular rules or do anything out of the ordinary, and it can take control of the robot and shut it down safely at any point that it decides to do so. We need to have it fall safely, even while it's carrying stuff, figure out how to do that, not fall downstairs, for example. And eventually, we're going to have enough trust in AI models after millions of hours of testing that we are going to trust the judgment of these things in order to, you know, not fall on a baby, in order to touch us in only the appropriate ways, use their strength in ways that will never cause damage, have robots that are actually helpers and allies, and are smart enough to do that. But it will be a while. This is an example. I want to point out, so in this sense, here's a person standing next to a stack of things, and a LiDAR or a depth camera. You can't tell anything. One of these objects you need to apply 50 pounds of force to because you're going to lift it, and one of these objects you're not allowed to touch. So how do you do that with like 99.999% reliability with a robot? Well, we're putting these human detection sensors on it, and it's this array of RGB and IR sensors, and you can see there's this epic array of sensors on the robot in order to just even get started on doing that. So when you see a humanoid robot and someone says, this is going to go in the home or this is going to go out into the world, look for an epic array of sensors, because that is a requirement. It is necessary. Now, once you detect the person, now you can choose the behavior. Right now, what we'll be doing is, before a person can get to it, the robot will sit down. So the robot can slow down as a person is getting closer and be in a lower and lower energy state until the point when it actually makes physical contact. It's in a safe state by the time the person gets there. That's the only way we're going to like walk down a hallway and be able to coexist in human spaces, even though we can't necessarily be right next to people at the very beginning. Nobody will be able to. This is the kind of thing that, again, TUV Rhineland, insurance companies, et cetera, really mandate this kind of approach. And then, we talked about varying loads. We carry a lot of different things, a lot of different kinds of totes, a lot of different things in the totes. We've got to get down on the ground safely. So we have some approaches to do that. And eventually, we'll trust these AI models through millions of hours of testing. And that's going to only happen once we have these hundreds of thousands of robots deployed in warehouses and then commercial environment back rooms, and then very gradually getting our way out into more and more unstructured, more and more public spaces. And, if you say in-home robotics is going to be a huge industry, sure, but it's also going to just hundreds of billions or trillions or who knows how big the market is on the way there. Like, we can just be moving bins and totes in a warehouse and have, a company worth billions just doing that task. Or we could probably have 5 or 10 companies worth, similar amounts doing just that task. It's such a huge market. And then we get out to just doing cardboard boxes, and unload tractor trailers and things like that. And there's so much to do on the way towards really impacting our whole economy, practicing with these robots, and eventually getting them just part of everyday life, which is so cool. So, to answer that question, what are the first commercial humanoids going to look like? They're going to be heavy, over 100 kilograms. The battery is going to fill up most of the torso, and the torso might be kind of chunky. It's not going to look just like a person. I don't know why it would, but it will be bipedal. It will have an upright torso. It will be bimanual. And it will have some cues that allow people to interpret the robot's intent and what it's going to do. And so you don't have to be trained to understand the robot. The robot needs to communicate on our terms as well because it's a human-centric machine. And I mentioned that epic sensor array and certifiable safety and all of those things. So not that human, but humanoid, as it turns out. So that's it. That's my talk. Thank you very much for listening. Questions? Anybody have some questions? And by the way, I would love some really challenging questions. This is a Stanford community. You guys know robotics, you know AI, so don't hold back. Ask me some good ones. Back.
Hi. Thank you for the great talk. It was like maybe one of the more convincing arguments for humanoids I've heard. I'm really interested in the interaction side that you were talking about and like integrating with humans. I'm curious what your thoughts are for moving from super conservative approaches to interaction, like sitting down when you notice someone coming, towards like these really like intimate settings of like carrying someone. Do you think that the path is mostly like software, or do you think there are hardware like changes?
It is definitely all of the above. So for example, we need the human detection sensors in order to even have software that can make choices about what to do when a person is there. It's going to have to get very, very good at knowing what forces it is applying and where before you can make choices about where you're applying that force. It's going to have enough awareness, not just that a person is there, but exactly the configuration of the person and what are like go, no-go zones. You know, you can touch a person here, other places you can't, that kind of thing. I think it's going to be just a long tail. I think that to start with, these robots will coexist with people, but they're going to be not right next to you. And then gradually you can be near them, but maybe only in industrial settings with people who are trained around the robots. And the robots do maybe slow down or pause what they're doing when the person walks by. And then very gradually, you know, then it works in the back room and grocery stores. And only the back room. And then eventually it's like stocking shelves, but at night. And again, around commercial grocery store employees are not going to be as trained as industrial employees. The expectations are different. So it's a little harder, a little more general, or maybe a lot. Then eventually they're out during the day, you know? And now they're starting to interact with the public. And you have to figure out that safety with the public. It's just going to be this long tail. And fortunately, I don't think that there's a big step that you have to do. I think that there is a continuum of gradually improving safety features and markets that you can then expand into as it gets a little bit better each time. Yeah, thank you. Good question. Here.
What do you think of wheels on feet?
Yeah. How good are you on roller skates? Maybe. And one thing I want to be clear is I don't want to claim that this is optimal. I want to claim that this is a very good solution, and we can definitely build a business around this. And maybe somebody will come up with a robot on roller skates that, you know, gets some of these use cases more effectively. I know that, you know, AMRs are better from going from one end of a warehouse to another. Digit's very good at loading and unloading and manipulating. So different features for different tasks. Here.
Quick one. Just what about human orchestrated humanoids? So I know
Human what?
Human orchestrated. So imagine I have 5 of these that I control them.
Okay, so the question is.
Decide that they're doing that thing. A human's there, you stop down. As sort of like an interim steps to the adoption of humanoids instead of fully autonomous.
So you're asking about how much do you want, like a lot of people and business models and ideas about teleoperating humanoids so that you can collect all of the data of how it's moving when people are controlling them and eventually have the robots controlling themselves, but start businesses with a human controlling humanoid. It's always going to have some layer of shared autonomy. There is always going to be some human in the loop. Like the Waymo autonomous vehicles are an example. It's pretty often, every couple of miles or something like that, that a person is logging in, you know, fixing some confusion that the robot has and letting it go, but it's very gradually and continuously getting better. And the same will be true for humanoids. Already it has to be shared autonomy because you can't, have you ever played the QWOP, Q-W-O-P? It's some Java game where you try to type using Q-W-O-P and get a little humanoid to walk. It's impossible. But you're trying to control each individual joint. You can't possibly. So for 30 degrees of freedom or more, you have to have the robot controlling its own balance and things. And then, can you joystick it around? Sure, we do. But it's going to be faster and more efficient to have it plan its own path in its own way. But through our ARC system, yeah, you can have your tablet. You can say, go here to this waypoint, pick up those, move this over there. That's a human interface. And then gradually, you know, you have less and less of that. No single answer. Yes, there will be lots of human interaction. I don't think, though, that the teleoperation is useful as a black box teleoperate robots, and eventually you learn how to control them. I think you have to do the RL and simulation, and that's actually more important, and maybe the teleop isn't even necessary for anything we want to do. Okay. Next.
Do you think companies like yours will innovate more on hardware and software, or do you think, or is it going to split at some point, or where do you see the industry going?
I think that because this is such an integrated system, it is really necessary to do all of it together as a holistic system. So, you know, even if we say want to buy a robot hand for this thing, well, the robot hand doesn't have quite the right, you know, sensors or quite the right power or quite the right size or quite the right configuration. You kind of have to understand the principles of the things and then design your whole product. I see it growing exactly like the automotive industry. There are going to be a lot of things that start to settle, and things like power electronics or electric motors or sensors or things like that, there's going to be this whole, supplier just pipeline and tons of companies doing that, just like in the automotive industry there is. Yeah, good. How about in the back?
So your manipulators seem to be distinct and heavily considered.
It's true.
They are different than what a lot of other humanoid type systems seem to use, which tend to go pure, five-finger replication. Can you speak to how you arrived at that particular, manipulator design?
Yeah, great. So the question is, why do we have 5 fingers? Why do we have the manipulator that we've got? And remember, we're trying to not build a humanoid, first of all. And just last week when I was here, and Rod Brooks gave a talk, and he just ripped into humanoids in general and all the hype. And one of his things, he's like, why do people have 5 fingers? And he showed a picture of like a fossil of the first creatures crawling out of the ocean, which happen to have 5 bones in their fins. Okay? So that history is why, probably, nobody really knows, probably why we have the 5 fingers that we have. And sure, we figured out how to make that useful, but that's not to say 3 fingers wouldn't be great, or 7, or some totally different configuration of a hand that's not quite so similar to a flipper. I don't know how dexterous trunks can get if there's enough evolution on those. So really what we did is, first off, we're going to have tool change mechanisms on our robots. People use tools all the time. We have the freedom of not being constrained to a general purpose 5-fingered manipulator to interface with the tool. We can have a nice, electrical interface and a mechanical interface. And our first tool is something that can pick up totes and move it around and do it reliably and grasp these things where there's like, you can have a 25 kilogram, tungsten ball rolling around in this bin. It's very hard to hold, actually. And so that's why we need to have these, these basically wide space so you can torque it, grasping things to really grasp the sides of the toes strongly. But I think manipulators, there's going to continue to be innovation for 100 years on how people do that. Yeah. 7.
Yes. You wanted some annoying questions.
Yes. I can count on you, that's right.
Why bother with legs? Since when you're showing the applications where you want to go to market the industry, they could be done with wheels just fine. And I can have 100 kilograms of batteries and compute down there. You will have 8 hours of power. You will not fall over. And you will be able to have a little telescopic thing up and down and get the same work.
I think that.
This is current. So my current annoying question to everybody with humanoids is just put 2 arms on a mobile platform. And I bet if you can't do it with this, you will not do it with a humanoid.
Okay. So I think that is the bet that Cobot is making. I think if you're doing 1 arm, that's what Stretch at Boston Dynamics gets you. I think that there are going to be successful configurations that are wheeled robots like that. So what I'm talking about specifically is you have to be dynamically stable because you need a small footprint on the ground and you need to be able to reach and lift heavy things up high. There are a lot of places where that's important. In the places where that's not important, you can use a Stretch robot or you can use a Cobot. And it has to be flat ground for those as well. So I think the other thing I want to point out is we are not a tote manipulation company. We are building multi-purpose, human-centric robots. We have a vision and a guess and a bet at what does it take to get robots kind of into everyday life and doing many, many different tasks for us. So where the versatility is really the value. When you can do lots of things, you now have to have that terrain capability in the stairs and everything else. You have to have that versatility. Again, maybe legs aren't optimal, but they're very, very good. We know how to do it. It will solve the problem. It will get out there into broad everyday use. Is that a good enough answer for you? It's okay. All right. Thanks. Allison.
I was curious about your thought about the need or lack of need for tactile sensing, fluid sensing on the skin of the robot, whether it's on the hands or other places in the body.
So knowing what forces you're applying is critical. I'll say that unequivocally. I think that we get 80% of the way there with very, very transparent actuators, where the actuators know exactly how much torque they're applying at a very high rate of control. So we do that with transmissions that are something like 95% efficient and as low a gear ratio as we can get away with for a robot of this scale, which is really hard, by the way. The little robots can do this because you can do like a 6-to-1 gear ratio. You can get enough power to weight ratio with small, but for a big robot like this, it takes more doing to get that kind of transparency. And I think we can make a lot of progress, do a lot of useful things that way. Like we can pick up the tote, we know how much it weighs, we can figure out its center of gravity. When we're sliding it off of a shelf, we know we can have a compliant interaction with the world. If the shelf is sliding us off in this way, it won't knock the robot over because we know the forces that are being applied. Eventually, I do think it's going to be important to have all the kind of skin sensors to detect slipping and enough information at the end effector where you're making contact to know what forces so that you're not confusing that with all of your inertial behaviors from the rest of the thing. My personal opinion and hypothesis is that we're going to get 80% of the way there without having to have all the tactile sensors and skin.
Can I touch a little bit on the body tactile sensor side? So when a robot falls on the ground, it seems like it might have some pattern of actions it goes through to get itself into maybe a known state. Would knowing about where you're touching the ground be helpful there?
Probably. I would say it's a policy. So there is compliance involved in how it moves. It's not just a position trajectory. And then, through dynamics randomization, you end up with something that's pretty stable and gets up almost all of the time. So we'll see how far that can go. And we do know how much forces we're applying. We just don't know exactly where that contact is happening. It may not be important to know exactly where that contact is happening. It may be important to just have something that's kind of self-stable. We'll find out. Back here.
So in terms of increasing application area, what software problem or what limitations in the toolset is most critical in your opinion?
Okay, so the question is, as we get out more broadly in the world, what are the real blockers in the tool set? The problem I'm interested in right now is, like we've shown that reinforcement learning and simulation can be translated to the real machine really, really effectively, and that we can outperform old-style model-based controllers, which is really the state of the art right now. Like all the best robot behaviors have been that up until like about now, maybe this last year. And we see this great cognitive intelligence coming down. That's just amazing. But that interface for how do you do the planning? How do you get enough of the context about when I'm picking something up, I have an estimate of how heavy it is, or I think that's a puddle, or things like that. How do you get that information down to a planner? And how do you learn a bunch of individual behaviors in simulation and then figure out how to connect those together in a smooth way in a continuum of behaviors? I don't think anybody knows how to do that yet. Sure. So did I show the picture of Cassie running? I don't remember if I showed that. We have a Cassie robot running, and it does a beautiful 100-meter dash. We have a behavior for it to do a 5K. We have a behavior for it to walk up and down stairs. But when it walks up and down stairs, it's picking up its feet pretty high because there's no perception. We don't have a way of transitioning between those behaviors. We just have the stair climbing behavior, we have the 5K behavior, we have the 100-meter dash behavior. All of these behaviors that you're seeing recently from like Unitree, Boston Dynamics, they're really amazing. They come from like motion capture or an animator, and then RL to stabilize it around that one behavior. So what they can do is press play, and the robot will do that one behavior. But how do you play basketball, right? How do you, on the fly, think about all of the tricks that you've learned and how to smooth them all together to create a whole behavior? Nobody knows how to do that yet. And that's been like a classic problem in robotics forever. My advisor called it sequential composition, and they were thinking about it when it was written down as just direct equations on paper to figure out how to do this. Same concept is applying to how do you link together AI tools as well. I don't know. That's one of the things that I think is a real challenge. And we'll figure that out. Adrian.
Yes. I appreciate the candor you said when you talk about safety. You asked for hard questions. Nobody asked a safety question. So I'm going to ask a safety question. You talked about tool use. You talked about some modularity. You haven't talked about, I think, the modularity in terms of the AI itself. So you talked about the long tail, it's something you learn from self-driving. In fact, you need to always be learning, updating the weights of the neural network, maybe even at test time. Even just managing your power budget for reasoning, test time reasoning. So can you talk a little bit about safety in the context of an ever-changing robot, not just the environment, but the robot itself?
Yes, thank you for asking that, because I forgot. Okay, one more question after this, because I forgot to mention, the good thing about having all of these in a hierarchy and different tools in different places is that some of these are very broadly general, no matter what robot you're using. Some of these are totally specific to the robot you're doing. And this makes training really efficient. So here, when we want to, say once we've figured out our whole body controller for our robot, the hard part is setting up the infrastructure. It's setting up all the cost functions, it's setting up all the training structure. Then once you press train on a few nice desktops, it goes in about a day, and then you've got it. So when you have a new robot, that's fast. This stuff is slower, but it applies to more broad robots. So the foundation models are more like in this region up here, and I think that's going to be applicable. So that means, you know, instead of having this big black box that you have to retrain this entire massive thing every time you make one change, it's not like that. You make a change, and you can just make small changes throughout your hierarchy, throughout your stack, for individual pieces or individual behaviors. And you end up with something that you basically press compile, and maybe it takes a lot more computational power to compile because you're training, but you have your whole system set up. I think something very similar will happen with the safety. Okay, one more question, and then again, we'll be out there for an hour, and you should just come talk to us. So, all right.
How do you reason about the speed of solving these tasks? So basically, like when you lift the box and then put it in the simulator,
Yeah.
like I would think it's way slower than a human doing that, at least at this point. Especially when it's trying to rotate it, that's way slower.
Yeah, it is slower than a human doing it. So the best initial tasks for us are ones where the human is not the blocker or the limiting factor in the speed of the task. So for example, the GXO warehouse where Digit is deployed right now, like actually, no, it's after the shift, but today it's had a full shift of working. The AMRs are coming up once a minute or something like that, and then Digit is able to pick up the box, put it on the conveyor, and then has to wait for the next AMR to show up. So those are the good first steps. But I mean, honestly, the speed with which our robot turns is terrible, and it's just a software thing to gradually improve as we solve the 10 million challenges from, you know, deployment. We'll be on that. They'll be much faster and continuing to get better and better. So, all right, thanks again, everybody.